If an estimate of the population standard deviation, sigma, cannot be determined prior to sampling, we use the sample standard deviation, S, to estimate population standard deviation, sigma. This is the sigma unknown case. In this case, the interval estimate for the population mean, mu, is based on the t distribution. When sigma is known, we use z. When sigma is unknown, we use t because S, the standard deviation of the sample, is used as an estimate of population standard deviation, sigma. For now, we assume data from the population is normally distributed. The t distribution is a family of similar probability distributions, all of which are symmetric and bell-shaped. A specific t distribution depends on a parameter known as the degrees of freedom. In this chapter, degrees of freedom refers to the number of independent pieces of information that go into the computation of sample standard deviation, S. Recall from chapter 3 that the sample standard deviation, S, is computed using an estimate of population mean known as the sample mean. If the population mean was known and used to compute the standard deviation, S, we would divide the sum of squared deviations by n, and the degrees of freedom would be n. However, since the standard deviation, S, is computed with sample mean x bar instead of population mean, mu, we divide the sum of squared deviations by n minus 1. So the degrees of freedom are n minus 1. As the degrees of freedom increases, because larger and larger samples are being used, the difference between the t distribution and the standard normal distribution becomes smaller and smaller. Below is the graph of the standard normal probability distribution. The t distribution with 10 degrees of freedom is shorter and wider. A graph that is shown in red. The t distribution with 20 degrees of freedom is shorter and wider. The t distribution with infinite many degrees of freedom, 101 or larger is considered infinite many, has the same shape as the standard normal probability distribution. For more than 100 degrees of freedom, standard normal z-values provide a good approximation to corresponding t-values. In fact, the final row of the t-distribution table, which is located in the appendix of most textbooks, is identified by the symbol of infinity in the degrees of freedom column. This row contains t-values. These t-values are the same as corresponding z-values. For example, notice a t-value of 1.96 has an upper tail probability of 0.0250. In the standard normal table, 0.0250 is in row negative 1.9 and column 06. Thus, for any given tail probability, t-values and z-values are identical when the degrees of freedom are equal to infinity. In our case, anything greater than or equal to 101. What are the t and z values corresponding to an upper tail probability of 0.0250? If the sample size is 11, the degrees of freedom equals 10. The value in the t distribution table associated with an upper tail probability of 0.0250 is denoted t subscript 0.0250. The t value is found in column 0.0250 and row 10, which is equal to 2.28. The probability that t is greater than 2.228 equals 0.0250 when the degrees of freedom is 10. If the sample size is 21, the degrees of freedom equals 20. The value in the t distribution table associated with an upper tail probability of 0.0250 is denoted t subscript 0.0250. The t value is found in column 0.0250 and in row 20, which is 2.086. The probability that t is greater than 2.086 equals 0.0250 when the degrees of freedom is equal to 20. If the sample size is over 101, the degrees of freedom is considered infinitely large. The t-value in the t-distribution table associated with an upper tail probability of 0.0250 is denoted t subscript 0.0250. The t-value is found in column 0.0250 and in row infinity, which is 1.96. The probability that t is greater than 1.96 equals 0.0250 when the degrees of freedom is infinite. If sigma is known, the probability that z is greater than 1.96 equals 0.025 as well. The interval estimate when sigma is unknown is equal to the sample mean x bar plus or minus the estimated margin of error, which is the product of the t-value and the estimated standard error. Like before, 1 minus alpha is the confidence coefficient. Like the z subscript alpha divided by 2, t subscript alpha divided by 2 is the t-value providing an area of alpha divided by 2 in the upper tail of the t-distribution with n minus 1 degrees of freedom. Because the population standard deviation is unknown, we have to use sample standard deviation S instead. Suppose you have no idea what the population mean and standard deviation are, and you need a best and worst case scenario estimates of the population mean. You can only randomly sample the population to compute these estimates. After randomly sampling a population 64 times, for example, 64 randomly chosen people tell you how old they are, the sample standard deviation and sample mean are equal to 11.5 years and 31.25 years. The first estimated standard error is thus equal to 11.5 divided by the square root of 64, which is equal to 1.4375. If your boss wants the interval estimate to provide her with 95% confidence, 1 minus 0.95 equals an alpha of 0.05. Since there are two tails in every interval estimate, alpha is divided by 2, which equals 0.025. The t-value is found in row 63 and column 0.025. Thus, the t-value equals 1.998. The first estimated margin of error is equal to the t-value times, which is 1.998, times the estimated standard error, which is 1.4375. The first estimated margin of error equals 2.87. After putting the first sample mean of x bar, 3.125 on the number line, notice how close it is to the population mean. In reality, you won't know this. Only your deity knows how close the first x bar is to the population mean. The upper endpoint of this interval estimate equals x bar, 31.25, plus the estimated margin of error, 2.87, which equals 34.12. A reporter for a student newspaper is writing an article on the cost of off-campus housing. A sample of 16 efficiency apartments within a half mile of campus resulted in a sample mean of $650 per month and a sample standard deviation of $55. Compute a 95% confidence interval estimate of the mean rent per month for the population of efficiency apartments within a half mile of campus. We will assume this population to be normally distributed. At 95% confidence, alpha is equal to 0.05. Because there are two tails in any interval estimate, we divide alpha by 2, which equals 0.025. The t-value is based on degrees of freedom equal to the sample size minus 1, which is equal to 16 minus 1, or 15. The t-value is in column 0.025 and row 15, which is 2.131. The interval estimate is equal to the sample mean plus or minus the estimated margin of error, which is the t-value times the estimated standard deviation, sample standard deviation, divided by the square root of the sample size. Recall the mean rent from the sample is $650. The t-value is equal to 2.131. The sample standard deviation is 55, and the sample size is 16. The interval estimate equals 650 plus or minus the estimated margin of error, 2930. or 620.70 to 679.30. The point estimate of the population mean mu is the mean rent from the sample. The interval estimate comprises two numbers, worst and best case scenarios. We are 95% confident that the mean rent per month for the population of efficiency apartments within a half mile of campus is between $620.70 and $679.30.